just
Sir,
observing the
excuse me,
list
sir.
that
They
so
are
many
saying that,
people are.
sir, excuse me, sir. They are saying that your voice is slow, but it is audible, madam. Please, participants, you also rejoin so that audible for us. You please rejoin. Thank you, sir.
Okay, okay. So now it is better?
Yeah, sir. Better, sir. Better. No problem.
Better. Okay, so because I'm going to talk about a very, very useful method. Okay. So I'm going to talk about the spectral method, but before going to implement the method and direct solving the OD and PD, I will just explain briefly in which that how we are going to solve and what are the basic steps involved in solving the OD and PD by using some method, means like a collocation technique, like a Gherkin technique, or basically you can also say that finite element technique, spectral element technique. But because today I'm going to directly concentrate only the collocation technique, so for that, in the beginning, I'm just going to tell you mathematically how we can solve so that you can enjoy the hands-on in the basically MATLAB. I will also use so many examples and you can directly solve in the MATLAB. So first I'm going to talk about that how we can implement the methods on solving basically any boundary value problem, basically mathematically. So just I'm going to share my slide. Just wait for me for a minute. Okay, let's just clear this one. Okay, sir. My
Yes, sir. Yes, sir.
PPT
Visible.
is visible?
Yeah, visible, sir. Visible, sir.
Okay, okay. So, okay. So now, as we know that when we are going to solve the boundary value problems or by using any direct techniques, which is basically listed in my next 2 or 3 slides, all this technique like a spectral collocation method or collocation method, subdomain method, least square method, Galerkin method, and finite element method, spectral method, these are basically based on the method of weighted residual. So first, you need to understand that what is a method of weighted residual. So because I have a limited time, so just I'm going to give you a glance of solving some ordinary differential equation. Okay. So now here, what we are going to do in a weighted residual method. Suppose your differential equation is dux plus p. This is given in equation 1. Derivative of u with respect to x plus some function of x is equal to 0. This is the d is a differential operator. It may be linear, it may be non-linear, but d is a differential operator first. And because here is a journal, so it may be any order here. So that's d is a differential operator. It may be linear, maybe because u is a function of x, so d is just I'm taking the ordinary derivative. So this is the equation. Then what to do in a numerical analysis? But because we are going to find out some approximate solution when we are just bounding to find the closed form solution or analytic solution of the problem. So we need to apply the basically numerical techniques. So when you are going to apply the numerical techniques means your non-variable should be approximated. And a non-variable is always approximated as given in equation 2 that any u, suppose u is a dependent variable, it's a field variable. Now we would like to find out the value of this u. So u is approximated by some another function which is given in the form of a series. This is given that summation I goes 1 to 1 ai phi ix, where ai are the constant which is to be determined, and the phi ix are basis function. These are known as a basis function. Basis function, as we have studied in linear algebra, that they must be linearly independent first. So their phi ix are our basis function. This is well-known function. We know very well that when we are going to approximate my field variable. So if this u is not exact u, and it is something is approximated value of u, so definitely when you are going to put u tilde instead of u, that your equation is not well satisfied, obviously, because it is not exactly u, it is just u tilde. It's not u tilde is equal to u, but it's approximately equal to u, for example. So when you are going to put this u equal to u tilde in the equation, then equation is not satisfied. There will be some error. And that error is also known as mathematically, that's the residual part. And this residual is, we are going to minimize this residual because our aim is to find out our approximate solution is very, very close to our analytical solution or our true solution. So that's why our aim is just to reduce this Rx. Rx means the residual. And in order to reduce this residual, what we are going to do, we use the weighted method. Weighted method means we are just going to multiply some function to the Rx and that integrate of the whole domain. So this is in our next slide. Means if your domain is omega, then Rx is a weighted, Rx is a basically residual part, and Wix is basically our weighted function. Weighted function is why we, it is natural ask that why we are not just integrating Rx dx, why are not taking only Rx, why are not taking Wix is equal to 1. This is also one question is arises here by the basically audience, but I'm going to explain the importance of this Wx. Actually, when we know that this weight is basically we put in this integration so that our integration is going fastly, it will converge very fast because we have studied that the convergence of the integral. So that's why we are going to put some function in the product of our integrand, and then that integration is going to be very, very that converges to very, very fast. That's why this is the most important thing in by choosing our Wx. And when you are going to put this Wx in this integration, and then this is equal to 0, Wix I'm taking here, not Wx. Why the Wi? Because if we go in the first slide, this is AI, A1, A2, A3, AN. These are our n unknown we need to obtain. And mathematically, we know that if we have n unknowns, then we can obtain n unknowns if we have n independent equations. So our aim is to find out n independent equations. So we have choice of taking weight function. So that's why this weight function can also be chosen as a drag delta function. We can choose the derivative of residual. We can choose as a basis function. So the choice of this weight function will distinguish our techniques. And how it can be distinguished. So I'm just going to explain in the next slide. So you will understand it. Okay, just see the here. If we choose a u tilde x is a basically C1, C2, C1 5-1x plus C2 5-2x plus C3 5-3x plus Cn 5x, that I'm going to write in a matrix form because I think this is the last day of this program, and basically I can assume that you know that a matrix is nothing but say mat plus this MATLAB is nothing but this is the amalgam of two words, mat plus lab. Mat is stand for the matrix and lab is stand for the laboratory. So that's why, and we also know that everything in the MATLAB we are using in terms of the matrix. So that's why we need to write everything in the form of a matrix. So our whatever the u tilde we have taken here, this can be written as a product of two matrices. That's one row matrix A1, A2, A3, and then another column matrix is 5-1, 5-2, 5-3, and 5n. So remember that whatever we are going to import in the MATLAB, that should be in terms of array or a matrix. It's okay. And if you are not getting anything, then you may raise your hand and ask me anytime during this lecture. Okay. Because today my aim is just to explain each and everything that how we can implement all these methods in the MATLAB. So when we are going to write this u tilde x as a product of two matrices, C transpose and phi transpose, means C is given here and phi is also given here. So we are going to put in the integration. So integration will again come because we have a choice that of phi 1, phi, the W1, W2, W3, and Wn, because we have to take n number of weight function, as we know that we have n number of variable, n number of unknowns. So to obtain that n number of unknowns, we need to have n independent equations. So we're just going to put all these things in this expression and integrating them. Definitely, we have n by n matrix, which is multiplied with a1, a2, 3, an, and which is equal to the some known function, because we know that in the beginning that this is px is known to us, so that will go into the right hand side with the multiple of whole w1, w2, w3, and w1, and integration over the whole domain. So our last equation will become this, And we know that this is very simply, if you are able to obtain all these n integral, n square integral, because n by n matrix, and we have our aim is just to evaluate these integral, and that integral can be very easily obtained by using some numerical technique also. And if you are going to put basically the analytic, basically the way of finding the integral as we usually do in a mathematics, you can also use the same thing here. But again, I'm going to tell you about why we are taking this W1, W2, because the choice of these weight function will always distinguish the techniques. First is a collocation technique. Today, I'm just going to talk about that one only. So, because other techniques I can explain, but it requires time. So, in the collocation technique, what we are doing, that W means that weight functions we are taking in the form of a drag delta function. So, what is that drag delta function? This is this one. Means whatever the Wix we are taking, this is nothing but we are going to take the drag delta function delta x minus xi. Means this center is xi, and x equal to xi, its value is tends to 1, because I have written 1, but it's not exactly 1, because this is tends to 1. But the people also define the mathematics that delta epsilon is equal to 1 upon epsilon when epsilon tends to 0 and the rest at infinity. So that's why, but that I'm going to writing here, that I'm writing drag delta function is here. Just simply at the point of xi, this is equal to 1 and the rest will be 0 in the whole domain. So that will give me a very simple implementation of the techniques, because as we know that xi are the points that's in the domain, they are split in the domain. So we take n point because our unknown is n, so we'll take n point in the domain, and they may be regular in the distance or they may be irregular in the distance. So here there are two choices. One we can take either it's a grid point at equidistance, and but you can also take at a collocation point, or basically collocation point are basically irregular in the nature, but they are coming into the domain. So when you are going to put this one, then we know very well, just come to the integral here. If in this equation 4, we are going to put Wix is equal to delta x minus xi, then we are going to use the integral property of drag delta. When you are going to put some function with the drag delta, that function should be integrable first. Because if function is not integrable, but we know very well that we are going to choose some function which are very small. Okay, so that will be always your residual is always integrable. So when you are going to put the drag delta here, then by using the property of drag delta, that whole integral will be nothing but the value of the residual at the critical at the basically collocation point. So the whole integral is going to be changed nothing but Rxi, because we know that integration from minus infinity to infinity fx into some delta x minus xi into dx is nothing but f at xi, means the integrand must be at the collocation point. So the whole integral is going to be replaced, means this whole system equation, this one, the first entry will be nothing but, this is nothing but Rx1. Second entry will be Rx2. Then Rx3. So that means all the integral can be very easily write that your residual is going to be 0 at all the collocation point. And you know that this your residual is going to be 0. Residual is containing n unknowns, and we have a n point x1, x2, x3, xn. When you are going to put first x1, then your one equation will come. Then you put x2, then your second equation will come. When you are going to put x is equal to xn, so that means your nth equation will come. Means you have n independent equations because your points are independent. Your points are basically distributed in the whole domain. So, okay. So now it means the collocation technique is a wonderful approach. Is whatever your integration is given in the residual, that can be directly converted to the system of algebraic equations. And that system of algebraic equation can be easily solved in a MATLAB by using very simple command. If you have a system Ax equal to B, then directly you can write x is equal to A/B, that your solution will be in your hand. But you will say that, sir, why we are not going to use the collocation technique only? Why you are saying that spectral collocation technique? So what is that difference? Just I'm going to explain within a minute. Then I will directly come to some problems. So because the approximation that whatever we are approximation taken here, this phi ix. If this phi ix we are taking like a polynomial, like a trigonometric function, like basically another hyperbolic function, that will depend upon the this situation or depend upon the types of a problem. If your problem is periodic, then your basis function must be periodic. But that's a different issue. But as mathematicians, we know that phi x we have independently, we have we have very many choices there. So if we have many choices there, that means automatically here there will be some that continuity and differentiability we are going to talk about here. If these phi ix are nothing but they are belong to the C infinity family. C infinity family, we know that they are continuously differentiable up to the Dirac order. Okay. If uh, if we know that if we replace these phi ix by the family of C infinity function, means they are continuously differentiable to infinity order. So our approximation solution is very smooth. And when it will be very smooth, so our error means that residual error, that residual part. When you are going to implement there, then we have a spectral accuracy. Spectral accuracy says that your approximate solution is very close to you, and it will depend upon this n, because as n is going to be increased, then it will very fastly converge to your basically exact solution, which is defined by you. So this is the basically simple approach here, but because as today that we are totally concentrating on the implementation on MATLAB. So I am coming to the MATLAB, but before that, just what is an spectral approach? We need to understand it. So now, if we have any participants have any problem in understanding the process here, then you may ask any questions right now, because I'm going to directly come to the approach of spectral collocation method, how to basically approximate our differential equation. And we know that in the differential equations can be approximate means we are just approximating our derivative in terms of something. Finite difference, we are giving in many forms, that either we are using central difference, forward difference, backward difference, whatever difference, or second order, first order. So it will depend. But in the spectral method, then how we can approximate our derivative. So I'm going to explain first that, and then directly come on the MATLAB, and you will enjoy the today the hands out and how we are going to solve the very basically a complicated problem within a line. Within 2 or 3 lines, you will have your solution. So do you have any problem, please? Let me ask to the audience. Yeah. Or shall I go on my another presentation, because in that I'm going to explain spectral method. Just within a 5 or 10 minutes, within 5 to 6 minutes, I will explain. So shall I go forward? Yeah. Hello. Am I audible or not?
Yes, sir.
So
Yes, sir,
now
audible.
Yes, sir, you are audible.
so if you have any problem, then ask to me. Otherwise, I will go on the next presentation. Okay, I think you don't have any problem. So, okay, so I'm moving. Just wait 3 minutes and stop here. Again, going to present that thing. Yeah. Is this visible?
Yes, sir.
Visible? Completely
Yes, sir.
visible? Okay.
Yes.
Okay. So here I'm going to solve. I'm just going to tell you that how we can approximate the derivative, or either ordinary derivative or partial derivative, how we can approximate it using the spectral collocation method, or how to explain by using the spectral technique. So here, just okay. Now, in order to use the spectral techniques, we have a several spectral technique. We have also we can use basically Legendre spectral collocation method, Chebyshev spectral collocation method. So there are several type of spectral collocation. They will depend upon the basically choice of a basis function. So here I'm going to talk about the Chebyshev. As we know that the Chebyshev polynomial very well. So I'm going to take the eigenfunction of the Chebyshev polynomial as our approximation. And you just don't concentrate on that what is that, but just I'm going to explain mathematically here, and then in the MATLAB everything is inbuilt. No need to write a separate program for the different Chebyshev or basically Legendre polynomial or Hermite polynomial, that you no need to write separate program because that is already inbuilt here. So what we are going to do here, because the Chebyshev polynomial is always the solution of the Chebyshev polynomial is always lie between -1 to +1. So what we are going to do, if your domain is from A to B, then domain A to B can be translated from to the -1 to +1, because our known variable is always -1 to +1. So if we have any domain, so that domain is also translated to -1 to +1, because all the collocation point here, collocation point is nothing but in this case they are the zeros of yeah, hello, zeros of eigen functions of singular Sturm-Liouville problem. We know that Chebyshev polynomial is a Sturm-Liouville problem, and that is a singular Sturm-Liouville problem, because that is 1 minus x square y double dash something. That 1 minus x square is going to be 0. That function multiple with the higher order derivative is going to be 0 at some point of the domain. Then that is known as a basically a singular Sturm-Liouville problem. But when we are taking the solution of that problems, so that is basically our base function. So here I'm going to write here, if we define here some unknown function phi xi, that can be approximated by g j xi and f xi. F xi means, you know, that beginning this f is unknown, the value of unknown at the collocation point xi I, and this g j xi, g1 g1 xi, g2 xi, g3 xi, and gn xi is same as basis function phi 1 phi 2 phi 3 phi 4. As we are going to put there, then we are writing this gj xi in terms of a Chebyshev function. And if you are writing in terms of the Legendre function, that will be Legendre collocation point, spectral collocation technique. But here I'm going to use the solution of Chebyshev polynomial, that is a TNX or TNJ. So that GJJ is basically this. This is already inbuilt in the MATLAB. You need no need to worry about this. What is that? So when you are going to put this here, so definitely this JJJ must satisfy the basically chronicle delta product. Means at all the grid point, Gj, Jjk must be delta Ijk. Means the value of this base function at the grid at the basically collocation point, it will be 1. At rest the collocation point, this is going to be 0. Now we are going to differentiate this function. Mathematically, we are going to differentiate this function as usual we are doing. And when we differentiate it, then we have some coefficient there. That coefficient is a, j, k. K is varies from 0 to 1. J is also varies from 0 to n. So that means this a, j, k is nothing but this is a n plus 1 cross n plus 1 matrix. And that matrix is here. This is that matrix. This is our differentiation matrix. So in a Chebyshev spectral collocation method, when you are going to take the Chebyshev collocation point in the domain, then differentiable means we are going to write the differentiation by the differentiation matrix. That is a Chebyshev differentiation matrix, which is written here. This is a Chebyshev differentiation matrix. If we have a double derivative, then what to do? Similarly, just multiply d into d, because d is stand for the derivative. So just multiply d into d, that is d square. If you have a third order derivative, then just do the power of 3. And if you have a n order of the differentiation, you just write the differentiation matrix d raised to the power n. It will give you the nth derivative of the function. Now I am directly come on the implementation of this method in a MATLAB. So I'm directly come to the MATLAB first, and here I'm going to solve all these problems. First, I'm taken second order problem. This is a boundary value problem where I've taken the different boundary conditions. The same problem, we can just change the boundary conditions slightly and your solutions directly change in a MATLAB. And then I have taken one problem. This is a basically Laplace equation, which is solved in -1 to +1 domain. And now with the condition that u is going to be 0 at the boundary. So now we need to solve this equation, and within 3 or 4 lines, again, you will say, sir, you are just solving only simple one equation. What is the importance here? But the same process can be applicable for solving the simultaneous equation. So here we have taken a one wonderful problem that is related to the fluid mechanics, but you can also use this technique anywhere else, because here I'm writing the simultaneous equation and with some boundary conditions. And I will also tell you that here how we can say that this our numerical solution is close to the analytic or not. Now, in order to take very toy problem, we are taking this one so that we know the exact solution. We know how we can find out the exact solution of the basically our problem. If you know the exact solution, we know the numerical solution, so we can compare them. We can find out the error, or we can plot them both in a one window. Then you will find the difference is okay, sir. We have some error, or we have very less error. So that's why I have taken today a very simple toy problem so that you can enjoy in the implementation of these spectral collocation technique in a MATLAB. So I'm going to directly come to the MATLAB here. Share advance. Is this visible?
Yes.
Is my MATLAB window is visible to all of you?
Yes, sir. Visible.
Okay. So our first question will be here that, sir, we are going to approximate the derivative of the differential equation by a derivative by a matrix. So can we compare it with our usual differentiation as we are going to do? So first I have taken very simple example in which I have some function, then I will find the derivative analytically, and definitely we find the derivative is using this spectral method. So what will be the difference? So first I have directly come to the this one program. This is the Chebyshev technique. We are going to use the cheb.m. That is already inbuilt in the MATLAB, that function, but I have written here in order to understand that how we can say that whatever we have written the mathematically, we can also implement in the computer. So just we are writing that matrix here, okay, whatever that I have shown in my PPT. So this is a differentiation matrix, and when you have an order means that order of the approximation capital N, as you are taking that capital N is 2, 3, 4, 5, 6, your matrix will be N plus 1 cross N plus 1. So now this is your differentiation matrix, means this is your derivative. This is the ordinary derivative. Now in the case of the partial derivative, I will definitely explain using the same differentiation matrix, but we write in a different sense. So now this is our differentiation matrix. So I'm going to write here first what is the differentiation here. If this is the differentiation, for example, I call this function d comma x is equal to Chebyshev n, because I don't know whether you know, we have understand how to make a function in a MATLAB, and it's just simply whatever the function is written here. Just see in the basically current folder. This is the current folder. Here you can see that how many files are there in the folder. Here we have written Chebyshev.m. That is a differentiation matrix. So I will write the name of that function same here. T comma x equal to Chebyshev capital N, means if you put n there 3, so you have a matrix D 3 cross 3 and 4 cross 4, and x are 4 collocation point. Automatically will give me the collocation point as well as the differentiation matrix. Now I have taken one function here, f is equal to sin x plus cos x. Then its derivative, you know very well, the sin x minus cos x, and I have find this y is nothing but d star f. Just simple. I'm not writing the derivative, just writing that this is our function. X is a collocation point. So x is a matrix. So sin x plus cos x is also matrix. So automatically this our f is also a matrix. So matrices means x is of what size? This is a, it depends upon n. And I have taken 29 here. You can take 5, 4, 6, 7, 8. I'm just taken for the trial is 29 here. I will also change them. So this f is again a matrix. So I'm just operating. We are going to write the first derivative of the function, means just multiply d with f. When I have written just below one line, df is equal to, this is our exact differentiation. What is the differentiation of this function? You know, this is cos x and minus sin x. This is our true differentiation. This is our exact differentiation of the function. But y, which is written at d star f, this is our numerical differentiation. So numerical differentiation means Chebyshev differentiation. So what is the difference between them? I am just going to write the plot. Plot x comma y, x versus y. X versus y is nothing but the Chebyshev differentiation, and then comma x versus df. That is basically our exact differentiation. So here I'm going to just basically I'm going to run this program, and then you will say that you will find the difference here. Okay. So I'm going to run this program here first. So this is our window is visible. Is the graph is visible to you or not? Because it is coming in front of me, but it may not come in front of you. Okay, so I'm just going to share here. Yeah, this is the differentiation graph. I think it's visible, huh?
Yes, sir, visible.
Visible. Just see in the program first. I'm going to actually in the online it's very tough to basically truly explain everything, because one by one you just need to change the window. So it's okay, but I will try my best just so that you can understand so many things here. So this is the basically that blue color, because I have not assigned any color there in the case of y, and that red dot is basically denote our df. Okay, so just coming to the our another the same presentation here. This is one. This y x comma y is basically nothing but the blue color. Means blue color is our differentiation, and our df is or. Or means when you have gone through the plotting of a graph in a MATLAB, and we have a several basically way of writing this one. Instead of r, if you're writing b, that will come color is blue. Then you are writing y, then the color will be yellow. And that's the same sense. But now you can say, okay, I'm going to change some functions, sir. Okay, you are writing e raised to the power x. So here, suppose I'm writing here some function, some another function. Someone's writing the product here, star cos x cos x. Okay, just I'm taking the product, and the product, the derivative will be what? What will be the derivative? Can you tell me? 0.5 star dot sine 2 x 2 star x. Okay, just this one. So I'm going to just run it. There will be a dimension error. Okay, so this is 2 star of this. This is star dot, because star is the stand for the product. But when you are going to make a product of some with the error, then with the matrix or with the array of some number, then you need to put dot also. So that's why I'm writing here. Okay, here. I'm just running this one. Not running this one. The matrix differentiation function line 3. Okay. Control Z if I'm taking here. Star dot. Control R. I'm just to run there whether it will be a problem. I think this is a problem in the product. Sin x is a matrix, then cos x is also matrix. So I'm just writing this one. Star is not coming. I'm taking another function so that we can check cos square, cos raised to the power 2. If you're taking cos x, let me see that. What is a cos x? The differentiation is sine. I will explain that's minus sine x. And if you plot it, then this one. Just see that what will come if we have this function. If just changing the function, then automatically your result will be changed. If I'm writing here this one, then automatically it is a blue, for example. So your result will come in the blue form. So, okay. So this is your choice that you are in what way you are going to explain. So this is the basically derivative.
Excuse me, sir.
Yeah.
OR and OB are same as B and R. OR is same as R. OB is same as B.
OB as same as
As B for blue color.
yeah, B is for blue color. O is just at the grid point, it's going to make a circle.
Okay, sir. Okay.
Clear?
Clear. It's clear.
Okay. You can also write here. Write this, for example, just writing semicolon. Suppose I'm not writing, I'm writing here red. This one. So you are getting your y is red with solid line, and your differentiation, exact differentiation is with blue line, but with the circle. Just see here. I'm just going to run it and just see the picture here. Your y is a red line, and your that df is your blue color circles. Okay, these are coming at the collocation points, isn't it? It's clear to all of you. Now let us come on. If we are going to find out some analytical solution, so what is a symbolic programming? Then because every time you no need to solve the equations by hand. You can also have a analytical solution by using, as you are doing in a mathematical, then you can also compute the analytical solution in a MATLAB by using the symbolic programming. For that, I'm going to take 2 examples, and by that you can understand how we can find the analytical solution or a closed form solution of some problems here. So I'm going to write here the first equation, that is analytic M. Yeah, this. Here I have taken one differential equation d2y by dx square, means double derivative of y with respect to x plus y equal to cos 2x. We know it's a solution. Is okay. But I'm not going to just do by hand. I would like to find out this is in the MATLAB always. Because when I'm going to teach this subject in either in MSc or either in some courses. So why should I will repeatedly find the solution if I'm going to change the boundary condition? No need to write. No need to solve several times. If you know the symbolic programming in a MATLAB, then directly you can have your analytic solution. Just see here how to use the symbolic programming in a MATLAB. First, you write SYMS, means this is symbolic programming. It is start that YX is our symbol. So you write SYMS. Just see the fourth line here. This is SYMS. This means the symbol YX. And dy is nothing but a difference. Write always differentiation. DIFF is a differentiation automatically inbuilt in the MATLAB. So T differentiation of y. Now I'm going to write how to write the ordinary differential equation. You just simply write the higher order derivative is equal to something. Means whatever the value is in your left hand, that you just transform into the right side, and you write the highest order derivative equal to some function. So here highest derivative is second order. So I'm writing d differentiation of y with respect to x twice. This 2 stand for the order. If it is 3 order, then instead of 2 you write 3. If it is 4th order, then instead of write 4. And this is equal to what? Cos 2x minus y. Cos 2x minus y. If instead of y it is a derivative, then you write differentiation of y, comma x comma 1. No need to write 1 because in the case we have defined on the differentiation of y. This is d. So this is an ordinary differential equation. Double derivative of y with respect to x is equal to some function that is cos to x minus y. अब अगर हमने if we have already written our differential equation, that means this ODE stand our differential equation. Now let us come on the boundary condition. I have taken two boundary condition here, that is y equal to -1 and 0 and y equal to 1 is equal to 1. Means our unknown variable is going to be 0 at the first boundary point or initial point, and this is 1 at our terminal point, that is equal to 1. So this is a boundary value problem because we have a two different point. We have a boundary from -1 to +1. The -1 is the initial point and 1 is a terminal point. So you can say that the domain is -1 to +1. So now we are writing condition 1, condition 2. If you have a 3, then condition 3, and then you write in the similar sense. If you have n order differential equation, you have n conditions, so write all the condition. But remember that when you are going to implement it, you write always in the matrix form. Just try to understand here. Our first condition is nothing but, I think, the derivative. This is the derivative here, dy. I'm not writing here dy. So this is our dy at 0 is equal to 1. Or just taking this one, y at -1. First I'm taking y at -1 or y at 0. This is 1. Directly change your condition as usual. Domain also change, boundary condition is also changed. Here my domain is from -1 to +1. So -1 is equal to suppose 0 and +1 is equal to again suppose 1. And I want to solve it. You write conditions. Conditions is a matrix which having condition 1 and condition 2. So that's why this is a capital bracket, condition 1 space condition 2. So this is a matrix of conditions. Now I'm going to write how to solve by using a simple command. Y solve x means solution of the differential equation in terms of y is equal to d solve. This is a one wonderful command in the MATLAB through which we can directly find the symbolic program or directly we find the analytic solution. So what d solve of what? Our ODE or PDE, because you can also find out the solution of partial differential equation. So here is ODE. So we are writing ODE is given there, and conditions. Conditions means whatever the conditions we have defined. Just simply write y sol is nothing but simplify y sol. Means if you are not writing simplify, it will give you a very basically large expression. And if you write a simplify y sol, means it will write a very close form solution. So here I'm going to write this one and going to plot one. So this is the running of this code. So this is our window here. Let's see here. Okay, it's coming, running. Okay, it's coming. Yeah. This I'm just saying that, yeah. Just see, this is a solution. This is your solution. This is your solution. And y sol is also here. Y sol is also here because it is some problem. This is the y solution. Is it visible, the solution? Here in the command window, is it visible?
Yes, sir, visible.
It's visible. So, okay. Now I'm going to change the boundary condition just simply in the code. Whatever the basically code we made here. This I'm going to change. Okay, I'm going to also change the domain. Suppose domain is 0 to 1. And the value at 0 is equal to 0. And the value of unknown at 1 equal to 1. So this means you have, this is a solution. This is your analytical solution. Just see here. It's creating some problem. Is it visible? Another solution. This is the solution of that problem, that as I have changed the boundary conditions, I have changed the domain just. So this symbolic problem is also wonderful because we can implement it and we can have the analytical solution of the problem. So this is also wonderful thing here. And you know that if we are going to write so many things several times, we are running our code, and this command window is basically filled with some result. But I don't want it several times. So you just try it in the beginning of the code is clear all and CLC. Right? Clear all and CLC. CLC means clear screen. When you are running this, you will have your current result only. This one is the current result. Just see here. Is it visible? Is it visible or not? I think it's visible, no? Okay. So now, this is symbolic programming. I'm coming to this next program. Then no need to write the next program, just to change there. No problem. Just change in the same program here. Whatever you want. I'm writing, okay, the condition
Sir,
is here is
actually-
-1. Here is supposed 2. So
Hello,
you
sir.
will have you. Yeah, hello. Are you asking something?
Sir, your screen is showing only graph, so please cut the graph.
Oh, sorry. Just see here. I'm just going to change the value here and running this one. So this is your analytic solution. It's visible. Yeah, Ashok, is it visible? Analytical solution.
Yes, sir.
Yes,
only
sir.
showing-
Sir, rotate,
Okay.
rotate.
Yeah. Can you pardon me? Are you asking something?
Sir, rotate window. The command of coding.
The command window is this. Now, is it not visible?
Sir, this is answer.
This is the answer. This is the analytical solution of that problem.
Sir, I want command.
You want command, na? This one. This
Yeah,
is,
yeah. Yes, sir.
Is it visible?
Yes, sir.
Just change the conditions and automatically your analytical solution will be in your hand. It's okay?
Okay, sir. Okay.
Okay. So if you have a third order, third degree, then automatically write condition 3. If you have nth order, then write the condition and okay. It's just a simple command. I will share all these codes. Okay. I will hand over to the Dr. Vinod Kumar, and he will definitely share all these recording to all the participants so that they can understand, they can implement, they can also use all these things in their research problem also. Okay. Not to be worried about it.
Okay, sir. Thank you.
Code will be in your hand, no problem. Code will be in
Excuse,
your
sir.
hand. Yeah.
Sir, please re-explain CHEB. HEB. Chep.
Chebyshev polynomial. Okay, I'm just going to explain it.
Yeah.
Chebyshev is this one. This is the differentiation matrix, what I have just shown in my different. Okay, I'm just you come here first. First, I'm going to come over here. This is our differentiation matrix. Just see the structure here. Cj.
Okay, sir.
Then -1 raised to the power k plus j, ck, jj minus jk. This jk is our basically collocation point. Means these are the x. X is I have taken in the code, not j, because j is not there. Na? So I'm writing x there. Just see this picture right now. And now you can take the screenshot and just compare with the code. You just take the screenshot of this one. Then parallelly, I will show that what I have written in the code. The same thing you will have there. Can I move to the code?
Yeah. Yes, sir.
Just come here, this code. X was our collocation points. So X is nothing but cos j pi upon n plus 1. So or cos j pi upon n. So this is cos pi. Our critical point is taken 0 to n. Just see here, n equal to 0 to n. If n equal to 0 and d equal to 0, then x is equal to 1. Remember, return. And if x is equal to these collocation point, then c is nothing but at c0 is 2, cn is our what? C1 is either +1 or -1. When this is the last point, this is at the last point, this is 2. At C0 and C capital N is equal to 2. Just see here. At C, what is the value of C? C is not written here. Okay, what is the value of C is nothing but C0 is equal to 2. C capital N equal to 2, and at the rest, this is equal to 1. So, okay. So now this is our code. Now I'm going to write what is another one. Another one is basically multiply minus 1 raised to the power 0 to 1. So this is the way of writing this C here. Now, what is dx? Dx is nothing but x minus x dash, and d is nothing but C in star 1 minus C dash. This is written in the matrix form. This one thing. This one is written here explicitly, but in that case, we have written implicitly. Implicit form means this is in terms of a matrix. We have written because everything in a MATLAB, we need to write in a matrix form. So every operations is basically we are going to implement in the matrix. So all these things is already inbuilt there. That is that code is made by myself. But you can also use only chip.m. That function automatically work, and that is inbuilt in the MATLAB, isn't it?
Okay, sir.
Clear? So now
Clear,
let us come here. So yeah, you may ask because the query will come, then I will enjoy lecture. Otherwise, one way delivery is not good for or not healthy for basically not healthy in the academic era. So
Ji,
that's
sir. Ji,
why
sir.
I welcome all the participants who will raise the questions. Okay.
Thank you, sir.
So I think up to this is you don't have any problem. I have explained in the first presentation that how to basically implement all these methods, means what is the weighted residual approach for finding the numerical solution of it. In the second, I would just explain simply how we can approximate the derivative by using the Chebyshev differentiation matrix. Just replace the derivative by the Chebyshev differentiation matrix, you will have your derivative of a known function. Now, if we know it, we also know that we can find out the exact solution of the differential equations. So now how to implement that spectral collocation in a MATLAB? For that, I'm going to write a very simple toy problem. This is our first problem. Yeah, this problem is simple first problem, this one. I think this is our first problem, toy y double dash is equal to e raised to the power 4x. I have written here. Okay, just see. This is the first toy problem. This double derivative of u with respect to x square is equal to e raised to the power 4x. This is our first toy problem, and I would like to solve it by using the spectral collision technique, and also we need to find out its analytical solution, and then we will compare with the numerical solution and analytical solution. So let us come and just see the code. Okay, so this is our differential equation. Y double dash is equal to exponential 4x, and it's because I have taken simply the domain from -1 to 1 in the sake of saving the time here. Because if we take a different domain, then need to translate from -1 to +1. So don't be just say that okay, sir, why you are taking -1 to +1 always? Because this will save me my time, because if I will write from 0 to 1, then we need to translate that from -1 to +1, then automatically your coefficient matrix is going to be change of the differential equation. This is the simply translation. So any domain A to B can be translated to -1 to 1 by using a linear transformation. Okay, so that f of A is equal to -1, f of B equal to 1, and f is a function ax plus or cx plus d. So c and d can be easily obtained. So that's it's not a big problem, but you just try to understand them how we can implement. The first is you need to write what is the requirement for solving the differential equation. The first requirement is the order of our approximation, because in the beginning I have written that u is equal to u tilde I equal to summation I goes 1 to n a I phi I x. So means that n we must know. So suppose that n is, in this case, suppose I'm taking 10. So this is a one input variable here. So you need to write what are the requirement here. What are the input variables? So n is the order of the polynomial or order of the approximation. So n we have taken 10. Now, what are the second thing? Second thing, that every derivative is going to be approximated by the Chebyshev derivative. So automatically we need to use the Chebyshev function. So write D comma X. This is second third line. D comma X is equal to capital CHEB N. It means if when you are taking N equal to 10 in the beginning, so automatically basically that command D comma X is equal to basic capital N will understand, okay, we need to generate a differentiation matrix of size 11 cross 11. So now means we have N equal to 10. So automatically our grid point will be 11. And if there will be 11, so our matrix will be of 11 cross 11. So now differentiation matrix is the second thing we need to write. What are the third thing? When you have suppose d2y by dx square plus some y is equal to some function, then you need to know that what will be the coefficient of y, because there is no derivative. If there is no derivative means there is an identity operator. So that's why we need to write an identity operator where differentiation is not there. So that's why I've defined I is equal to E by E. It is, I think, if you have gone through the matrix analysis in the MATLAB, this is already defined, that identity matrix, random matrix, all these matrix, this is a zero matrix. Okay, how we can write the diagonal matrix, how we can write it. So this is EYE stands for the identity matrix of size n plus 1. N plus 1 means 11 cross 11, because we need to compare, we need to maintain the dimension of the matrices also, or dimension of the array in a competition. Now, what is the derivative involved here? What is the derivative involved here?
Double
Yeah,
Two.
2. So we need to write the product of this B matrix twice, or the power of B is 2. So here D2 I have written, D2 means second derivative is equal to nothing but D raised to the power 2 means D star D, or D multiply with D. As we are writing in mathematics, D by dx over D by dx is nothing but D2 by dx square. That's operator, differential operator we are just writing. In the similar sense we are going to write here, because that will give me the logic that, okay, double derivative is nothing but D over D. So D is a differentiation, D another differentiation operating on both. So D into D is D square. So this is D square. I think up to this, you don't have any problem in the implementation.
Sir, here one has raised a doubt. Why we have taken capital N is equal to 10? Someone has raised it.
Oh, you can take element, you can take two, because this will give me the approximation summation I goes 1 to 1. If you are taking 5, okay, no problem. As your n is going to be increased, your solution is going to be converged to the your true solution, because whatever you are getting numerically, that is a basically numerical solution that is very it should be close, because we need to minimize the error. So n agar if you will take n is very less, so your grid point will be sparse in the whole domain. So you are not getting the exact picture of the solution. So you are taking that n, and for that you need to find out the independency of n. It will depend upon the accuracy of your solution. I want to find the solution, accurate solution of the four decimal. So maybe that n is equal to 15 will be sufficient. Why you are taking 20? Why you are taking 25? Only 15 is sufficient for 4D. But somebody will, okay, I know I want the solution up to the 7 decimal, not 4 decimal. So up to 7 decimal, you are going to increase your number n. Suppose you are getting, okay, n is equal to 30 is sufficient for getting the 7 decimal accuracy. So it's okay. So n, that's why we can vary. N is a number which is basically denote the order of approximation. Up to what order you are going to check. Is it
Another
clear?
question, someone has raised that. What is the
Yeah.
meaning of REP-MAT? REP-MAT, REP-MAT, someone.
What mat?
In chat box, someone has raised a question. What is the meaning of REP-MAT? REP-MAT something.
REP.
In chat box, you can see, sir.
Okay, just let me see the chat box. No? Okay, more in the chat box. Okay, yeah, this chat box. This is what I'm not just in the last I'm coming. Okay, I'm not seeing somewhere else. What is the n? Okay, why, sir? Why we are taking n equal to 10? This is okay. It is observed, and we are taking just to increase or taking the accuracy. One message is there, sir. What is the meaning of rep matrix? Where you have written rep matrix?
I don't know. Someone has raised that question in chat box. That's why I repeated same question.
Okay, what is the Chebyshev function? It's okay. Chebyshev function means the whatever our Chebyshev differentiation matrix, because that will depend upon the Chebyshev collocation point, which is xi is equal to cos pi j upon capital N. J goes vary from 0 to n. That is Chebyshev point. They are nothing but they are the solution of Chebyshev function. Whatever Tnx is a solution means they are the solution of Chebyshev functions. That's why we need Chebyshev. If you want to, okay, I'm not interested to take the Chebyshev polynomials, or we have alternative that you can take Legendre polynomial. So that means you need to just change it. Instead of Cheb is Legendre. LEG. That's sufficient. It will give me the Legendre, the solution of the Legendre functions Pnx. The roots of the Pnx is our collocation point. Here, roots of Pnx is a collocation point. So that's why Chebyshev is means we are taking the collocation point as a roots of the solution of Chebyshev polynomial. If you are taking the Legendre polynomial, then you need to change the name even, because that function is different, because we are going to take the different the basically zeros. We are taking the zeros of Legendre polynomial, then you need to take the Legendre differentiation matrix. There are different kinds of the differentiation matrix in the spectral method. It's clear? But I'm not writing I have not written somewhere the RAP matrix. Okay, let me see that whether it will come or not. And who is asking this question? So he may talk to me, na? He or she may talk to me. Who has written this RAP matrix? I think I'm not written somewhere else RAP matrix.
Okay, leave it, sir. Again, no problem.
Oh,
We
okay,
can proceed.
okay. Otherwise, the platform is open for the discussion, huh?
Yes, sir. Yes, sir. Yes.
Okay. So now we know that n is order of the polynomial. We have written it. We know the differentiation matrix we required. We have written the differentiation matrix. We know that somewhere else if some unknown variable y is written, okay, then what is the coefficient there? The coefficient is not a differentiation matrix. So d raised to the power 0 is a differentiation. We say that dy by dx is first order. If we are writing only y, means there is no derivative. So that means the power of d is 0 means automatically we say that's identity matrix. Here we are just writing in that sense 1. 1 is nothing but in the matrix. In matrix, that is the identity matrix. So identity matrix we have used. We have used the double derivative, means we are just getting the double power of the matrix. Now, what is our forcing function? Forcing function is what is in our right hand side given to us. In this case, the exponential 4x is given as a forcing function. So we are writing this capital F is equal to exponential of 4x. So now, it just simply we have written the matrix. But we have not implemented the boundary condition till now. So how to implement it? In a spectral method, when you are going to solve it in a one-dimensional, at a first grid point, first -1 is nothing. Just write cos j pi upon n. At j is equal to 0, what you are getting? At least someone of you must be communicate with me. Cos pi j upon capital N. J vary from 0 to n. If j is equal to 0, then what is the value of cos pi j upon n? That will be 1, I think. It's okay?
Yeah. 1.
That will be 1. That will be 1. What is the value of cos pi j upon n when j is equal to n? That is cos pi. Cos pi equal to? What is the value of cos pi?
-1.
-1. So it means our first grid point, our first domain, when you are going to put j is equal to 0, that means you are getting the last grid point, that is 1. When you are getting j is equal to n, then you are coming to the first grid point. Means you are moving from last to the first. It doesn't matter whether you are taking from -1 to +1, then this is another translation. But as usual, it is there. That will be the same. It will manage automatically. So means when your grid point is 1, means here, because in a MATLAB you know that 0 is not started by taking any loop. Any loop is started from 1 to n, 1 to n, not 0 to n. Okay, so that's why here 1 stand for your first j is equal to 0. So, okay. So at the first grid point, what is the value? At the first means the last point. Last point पे क्या है? What is our condition? Just see, we are taking the mixed boundary condition here. Y dash at 1 plus y at 1 means the derivative is also involved in the boundary condition. If the derivative is involved in the boundary condition, definitely we write a d here. Just simply write whatever d1 dot there, d1 dot here at y plus y at 1 means identity matrix multiple with y means identity matrix. Identity matrix, instead of the entry you are writing same 1 comma semicolon. That means it's going to be changed the whole row at 1. And similarly, we need to change the whole row at -1. So at D2 n plus 1 at the last grid point means our first grid point. In the loop, j is equal to n plus 1 is nothing but the last grid point, and at the last grid point is nothing but a -1. So what is the boundary condition is 0. So I'm just writing this is equal to 0 here. I think it's not 0. Identity we have written here. Identity means 1. So according to this boundary condition, I'm writing this is 0. I have written in a different sense because we'll change different boundary condition. Will writing just different, just slightly change in the boundary condition. So this D2 here, this written I already written here. This is written in the by taking this basically on command boundary condition y dash at 1 plus y1 equal to 0. So this is replaced. The whole row at that grid point is going to be changed by the condition, and at -1 is also going to be changed, and that is equal to 0 here. So, okay. No, this is the first side. So I'm writing identity. This is the matrix in the first case here. What is the coefficient of y here? What is the coefficient of this y at -1 here? This coefficient is 1. This coefficient is 1 or not? 1. So that's why this we are going to write identity matrix. Now, what is in the right hand side? It will depend. In the first boundary condition, right hand side is 0. So f1 at 0 is equal to 0. And what is the basically the right hand side of the second condition? This is again 0. So we are writing f at n plus 1 is equal to 0. As we are going to change in the left hand side, similarly we are going to change in the right hand side. Right hand side is nothing but a forcing function. f1 at 0, fn plus 1 is equal to 0. Now you have a whole matrix. Your matrix is D2 is with you. Your matrix F is with you. And the system is coming D2 into some coefficient is equal to your forcing function. That is a system of AX is equal to B. And that can be easily solved y equal to D2 slash F. This is the criteria. And if it is the criteria, then out, what will be our analytical solution? So analytical solution, I just write simply code there because you know very well that we can write symbolically form. So I have run the code symbolically and I have obtained that solution here. This C1, C2, C3, whatever I have written, this is there. So exact solution is also written here because I'm not basically taking so much time finding with the help of symbolic. I have written the solution by using the symbolic programming. So this is our exact solution written in the below. Just solve y equal to d2 slash f. It will give me the solution y. And now we are going to plot it. Just run the code and you will have the solution. You will have the solutions. Okay. And okay, I'm going to show you. This is your solution. How many points I have taken? How many points we have taken? 10 points. Just see. Okay, let me take and I'm just going to modify so that it will be easy. Okay, I'm taking OR. OR means red circles and add the analytical solution. I'm just going to write, yeah, this is your result. Is it visible? Is it visible or not? Okay, again, I'm going to change slightly.
Visual.
Yes, and okay, and this plot I'm going to take here, comma, hyphen minus B. So this color is B. Okay, so your analytical numerical solution is of color B, and your exact solution will be of color red with circle. So just see in the picture. I'm going to share here this one. It's clear? I think easily you can distinguish. And just see here, it's very, very, very close to the exact solution because directly coming on that system. I'm just writing, I'm going to increase n because some participant have asked that why we are taking n equal to only 10. Okay, it's your choice. I'm going to take 20. If I'm going to take 20, so what will happen? Just see here. Your solution will be this. If you are taking n equal to 100, no problem. You can take 100. Okay. Just coming to my screen. If this is 100, then no problem. This is your final output. Clear? Is this clear to all of you?
Yes, sir.
And
Yes, sir,
okay,
clear.
you can write X label, Y label, and title. It's very easy, and you can just see in any book of the MATLAB, you can write. Now, but this is a way that we can solve it. Now I'm going to change the boundary condition in the same code, and your solution is going to be changed. So I'm taking another problem here. So I think this is coming to there. Yeah. So I'm taking OD2. Here, what we are going to take? Here, I'm just going to take the derivative simple.
Sir, excuse me,
Yeah.
sir.
Yeah.
Sir, please change the please explain the what is the change when n equal to 10, n equal to 100 in graph. In
In
graph,
graph,
what is the
that is the grid point. At what grid point you are getting the solution? If you are taking n equal to suppose 5, so your
okay,
grid
sir.
point will be 6. Your grid point will be 6. So you will have the 6 point. 6 point means the value of unknown variable at a 6 point. You can match with your analytical solution. If you are
Okay,
taking n
sir.
equal to 10, so the grid point, whatever you are taking in the domain, that is 10. If that 10 values you are having of unknown variable, because in a numerically we are solving, we are not getting some function. We are getting the numerical value at the grid points. Okay.
Okay. Okay, sir.
So
Clear. Okay.
here in this
Thank you, sir.
case, what we are taking? Here we are taking 100 points, 100 grid point in the domain. So we have 100, the value of unknown at the 100 grid point. That is given 100 values. Is okay?
Sir, 100 or 100 plus 1?
100 plus 1, 100 plus 1. Yeah. If you
Yeah,
take
yeah,
it,
yeah.
that is n plus 1 always directly. 1 plus order. Okay.
Yes.
So
Yes, sir. Yes, sir.
here the same equations we have taken, but the derivative, instead of this, we have taken the derivative. And it is, I think, much easier rather than the previous problem. The same, and is taken anything, it's your choice. The derivative matrix, second derivative, your forcing function. Now, what is that? Your last boundary condition. Last boundary condition is in the left hand side, the coefficient is derivative of the matrix. So we have written derivative at the last point. Okay. And what is your first point? What is the value of the first point? What is the value of the first point? This is 0, na? This is coefficient is 1. So that's why we are writing 1 here. And at the last point, this is going to be 0. So if you feel writing this one, so this code I have taken is very this is a generalized code. I have written so many boundary condition and so many solution here. So if you run this code, so we are getting this solution. It's okay. This is the solution when we have taken this boundary condition. Written here exact solution also, y at -1 is equal to 1 and the derivative of y at 1 equal to 0. Just see this, y at -1 equal to 0 and y derivative at 1 equal to 0. So now if I going to change it, suppose I want to write this condition. This first, y at -1 is equal to 0, derivative is also going to be 0. So your exact solution is this. So I'm going to just making this is a command. So you will have exact solution is this. Y at -1 equal to 0 and derivative is also going to be 0. And what will be the change? this is d2 n plus 1 is equal to 0 and d2 n plus 1 plus 1 is also equal to 0. And this is again d11 is equal to 1 and f at 1 is equal to also 0. Right hand side means forcing function at the grid point is going to be 0. And this is 1, this is again 1 because that will be 1. So I'm going to write this one. So this is your solution. Okay. This one is your solution. Visible? In the same domain, the another solution. Because I put the command hold in order to tell you what is the difference of the first by taking first boundary condition, what is the difference in the same solution of the differential equation by taking different boundary condition. Just see here. If you are going to take another boundary condition, like this is 1. So your exact solution will be this. So I'm going to make it.
Code is not visible.
Okay, I'm just writing this thing. This is visible now. Just
Yes,
changing the boundary condition according to I'm just going to write it. So 1 1. Okay, so 1 1 is there means forcing function will be 1 1. So instead of 0, this is 1. Instead of 0, this is 1. And run it. What is that accepted? -1. I think something being wrong. Okay, here. Yeah, this should be on command. Na? Yeah, now it will come. Definitely it will come and your solution will be this one. This is the third solution, third boundary conditions. Okay. Because as your boundary condition going to be changed, or definitely your solution is going to be changed. And just see in all the picture that our grid point, whatever we have taken it, here we have taken 25. So at the 25 grid point, we are exactly matched to the exact solution. It means this convergence is very fast. After taking a very less number of grid point, we are having very close solution to the exact. This our numerical solution is very, very close to our exact. This is the beauty of a spectral technique. Spectral technique means we are getting spectral accuracy. Spectral accuracy means your result is going to be very fast and it will be close to your exact solution. This is the basically the most important thing while using. And the collocation is automatically collocation you can choose in anywhere else, but the collocation directly translate your whole integral to the direct differential equation to your set of algebraic equation. No need to write several times the integration. You no need to use the integration as inbuilt trapezoid rule or Simpson 3/8 or Gaussian quadrature formula. No need to write anything. If you are using the spectral approximation, just take the collocation point. That will give me a very, very simplest way, even in implementation as well as in the result. So this is the way that we can implement this one. So I think up to this, if you have any problem, then ask to me. Otherwise, I will go then how to solve the partial differential equation and within a just few lines. Yes, anybody have any problem? So I will explain. Can I go on the Poisson equation because that was my last toy problem.
Yes, sir.
Okay. So let us come. What is the way of implementing the solutions of some partial differential equation using the same technique? Actually, we know that what we are doing when we do the partial differentiation. The same, actually, whatever we are doing in the computer, that is the same thing as we are thinking mathematically. So we know that when you are going to find out the partial derivative of some function fxy with respect to x means you are taking y as a constant. We are not touching anything. We are not doing anything in the expressions related to y. We are just bother about the differentiation with respect to x. But is another way that of the differentiation, we are using the same formulae as we have studied in the differentiation usually. If we have x square and we want to find out the derivative, that's 2x. And if we have the differentiation is function is x square y square and we need to find out the partial derivative of x square y square with respect to y, then you will say X square is a constant and the derivative of y square is with respect to y is 2y. So we need to understand this concept and then we need to implement in the form of a canonical delta. Those people have gone through the tensor analysis. They know very well what is your canonical product. Canonical product means the product of two matrices. Canonical product means it's just not a usual matrix product, as we know, slightly different. But it's a tensor product. Tensor product means, you know, if matrix A and B is given to us, suppose I'm giving an example here. I'm just writing here an example. Suppose A matrix is equal to 1 space 2 and semicolon, suppose 3 space 4. This matrix is with me. A is visible? A is visible or not?
Yes, sir.
Yes, sir. Okay. So now I'm writing B equal to another matrix, suppose 1 space 2 space 3 semicolon 1 space 4 space 7 semicolon 3 space 6 space 9, and this is your B matrix. Is clear? A and B with us. Just see here, the order is not changed. Order is basically different. So their product is not possible. Matrix product is not possible, but canonical product is possible. I'm going to write what is a canonical product. This is a cron product, okay? Control C, I'm writing here. Okay, just my screen is very, very small, so it will create. Just see here, some matrix, not AA is equal to canonical product of matrix A with B. What is our result? What is our result? See? Can you say, can you conclude something? Just I'm going to explain in front of you. What is your matrix? We are multiplying A with B. A with B, na canonical product of A with B. It means we are multiplying each place of this one, every element of matrix B. We are going to replace the matrix A with the product of that element. Just see, this is a one element. At 1 will be 2 by 2 matrix A, 1, 2, 3, 4. If we multiply by 1, that will be 1, 2, 1, 4. What is that? 1, 2, 3, 1, 2, 4. Okay. This is nothing but this whole matrix B. Not visible completely. Let me just see here. Yeah, not is complete. Yeah. You replace this matrix capital B at 1. So this whole matrix will be at 1. The same matrix is replaced instead of 2. It's twice multiple. What is the twice multiple of B? Twice multiple of B, 2, 4, 6. So this is 2, 4, 6. What is the second row? 2, 8, 14. What is the third row? 6, 12, 18. It means this first entry, first 3 by 3 matrix, if you had consider here, this is a one multiple of matrix B. Yani ki where A is written, A11 multiple the whole matrix B. And instead of the entry A12 multiply with the matrix B. And A21, instead of A21, it is a matrix. A21 multiply with B. And what is A22 position there? A22 multiply with B. So it means at every positions you are getting 3 cross 3 matrix, and we have a 4 position. So this will be 6 by 6 matrix. So that's why this is your canonical product, and you are having this one. Just see last entry, this one. The first 3 entry 3, 6, 9. Multiply the matrix B with 3. 3, 6, 9. 3, 12, 21. And that 9, 18, 27. And the last entry is multiply with 4. 4, 8, 12, 4, 16, 28. And multiply by 4 here, so 12, 24, and 36. This is the process that, okay, chronicle product is similarly is a tensor product. That one matrix is a tension, another matrix is also tensor. We are going to just multiply them. If we are writing reversely, because it is most necessary to understand this criteria while you are going to study the solution of a partial differential equation using spectral collocation technique. So I'm writing here some VB equal to Cron product. Cron means it will directly come from the history, or Cron product of, I'm interchanging this one, B, comma, A. It means at every entry of B, we multiply a matrix A. Just enter. And both are not same, both are different. At the first entry of the matrix B, you will multiply with the matrix A. Just see here, it's a 1, so automatically B will be there. The second entry is 1, automatically B will be there. This is 2, instead of 2 will be twice, 2 multiple of each element of B will be there. Just see here, this matrix is different product. Chronicle product is also not a symmetric. It's not satisfy the symmetric property. A chronicle product of A with B does not necessarily equal to the chronicle product of B with A. It's okay. But we know that very well. If A cross B or A dot B is not possible, chronicle product is possible. So we are going to implement the same idea, and differentiation we know very well. Chebyshev differentiation matrix with me. So we'll just replace, where is the derivative with respect to x? We replace the differentiation same matrix with the multiple of identity, chronicle product of I. Why we are going to multiply the chronicle product? Because y is constant. If y is constant, then your first matrix will be dx, differentiation with respect to x, comma, identity matrix. It means your y is the same. We are not going to change anything in y. And if your differentiation is with respect to y, then your first position in the chronicle product will be identity. That x is fixed, comma, dy. Dy means nothing but the same differentiation matrix. So because we are doing the differentiation does not depend. We are writing differentiation with respect to differentiation with respect to other. That rule remains the same. So when you have a mixed derivative, then what to do? In the mixed derivative, we have a chronicle product d stacks, comma, dy. Whatever you have just written. Just see the one example. Through that, I will 100% deliver that you will understand how we can find the solution of a partial differential equation using collocation technique. Just see here. I'm just making this one large. So is it visible? The screen is visible or not?
Yes, sir. Yes, sir. Sir. Yes.
Yeah, understand. And
More how much,
as we know very well that, okay, so what will be our grade point? So, okay, I will say that, okay, grade point is taking 24 and taking 20, taking anything else. So here I'm taking, for example, 30. In this case, I'm taking 30, no problem. Then again, you need a differentiation matrix. So d comma x is equal to Chebyshev of n. This is in with your hand. I'm taking y equal to x. Why I'm taking y equal to? I'm taking that, okay, same number of grid point in the x direction, same number of grid point in the y direction. If you are taking n in x direction, so I'm taking n is also in y direction. It's okay. Now, what to do? If you are n plus 1 grid point in the x direction, n plus 1 in the y direction, so what are the total grid point in your domain? Because your domain is minus 1 plus 2 plus 1 cross, minus 1 to plus 1. Just see here when I've defined this problem here, this is the second toy problem. Okay. This second toy problem, just see here. Is it visible? This one? The 14. Del u by del x square plus del u by del y square. It's a y square, not y. Okay, type of mistake. Is equal to 0 in the domain minus 1 to plus 1 cross minus 1 to plus 1. And while I'm taking all the boundary is this u is going to be 0. So this equation I'm going to solve here. So now what we need here, we need, since we have a number of grid point is n. So by taking x is a number of collocation point in x direction, y is also same collocation point. So we need to its product, because we need to find out if suppose at x equal to 1, we need to find out the value at y equal to, so there will be coordinate 1, 2, 1, 3, 1, 4, 1, 5, 1, n. Then 2, 1, 2, 2, 2, 3, 2, 5, 2, n. 3, 1, 3, 2, 3, 4, 3, n. Similarly, n1, n2, n3, n4. So this is, we need to find out the, basically, the mass grid. Mass grid of what? All the product of the points. So let's we have a domain is square domain -1 to +1, -1 to +1, and that means we need all the grid points located in the domain. So this, the process of that, we are going to use a mass grid. This is also wonderful command in the MATLAB, through which you can find out the grid product. So this is a mass grid of x 2 to n and 2 to n. Why taking 2 to n? You will say, okay, because at the boundary we know that at the boundary is some grid point at basically x equal to 1 and x equal to n plus 1. So I'm not touching the boundary. I'm just taking all the grid point inside, that is 2 to n and 2 to n, because our grid point is 1 to n plus 1. So I'm just leaving the boundary points here. As usual, we do in the ordinary differential equation. So this one, x is equal to x column. I'm taking column, that is a derivative with respect to x. Or no, not a derivative, it's collocation point with respect to x. Y is a collocation point with respect to y. Now, what if we find the numerical solution, then how we can compare it? So we need to have its exact solution. So here I have written exact solution. F is equal to tan into sine 8x star y minus 1. This is a harmonic function. If you will find that this is a harmonic function. Harmonic function means who's satisfying the Laplace equation. Every harmonic function is a solution of our Laplace equation. But if I will give the difference, the boundary condition, so we need to also implement the boundary condition so that you will have your same harmonic function. Harmonic, the solution of wave that Laplace equation is a harmonic function. So this is, I've taken simple one harmonic function who's going to be satisfy all the boundary condition at plus minus 1 is going to be 0. Again, what to do? We have a second derivative with respect to x, second derivative with respect to y. So we require the power of 2 of t. So this is d2 is equal to nothing but double power of this. And d2 I'm taking 2 to n, 2 to n, not taking all the grid point of the boundary, because at 0, at 1, you are having x is equal to 1 means at x-axis, all the grid point. If you are taking x is equal to for n plus 1, that means the upper domain, and left of the x-axis, y-axis, and right of the y-axis. So I'm just leaving all them. So that's why 2 to n we am taking. Identity matrix is where is a unknown variable is kept there. If the coefficient is 1, then you are using the identity matrix. Now, what is our operator? Operator says that uxxx means the double derivative with respect to x, means instead of x, we are going to take d2, and instead of y, we are going to take identity matrix. So this is L equal to nothing but chronicle product of I into d2 plus chronicle product of d2 into I. It means that uxx plus uy is written. If suppose there is uxy in some equation, so you will write chronicle product of d2 comma d2. It means this is the derivative with respect to x, differentiation matrix with respect to y, and we are going to make its product, chronicle product. So this product will give me the left hand side, nothing else. Just L is our left hand side. What is our right hand side? Can you tell me? Yes. Here I'm taking, suppose this forcing function, this is not a solution, this is a forcing function I'm taking here. So this is forcing function, all the value of this forcing function is this. So here I'm going to write, I'm not going to solve the Laplace equation, I'm going to solve the Poisson equation. Del u by del x square plus del u by del y square is equal to some function f. This is the basically Laplacian equation, but not homogeneous, inhomogeneous. Inhomogeneous means That inhomogeneous Laplace equation is also known as the Poisson equation. Poisson equation, because we all know I'm the person of basically fluid mechanics, so I will say that the heat conduction, okay, heat conduction in a plate, that study heat conduction in a plate while we don't have any other that forces function. So that's a Laplace equation. And if you are going to find out the heat conduction in a plate with some forcing function is there, some temperature is there, that is a Poisson equation. But study case we are going to take, because otherwise the derivative of a non-variable with respect to time will be there. But all these story I'm not going to tell you in front of you. You just think that this is a our Poisson equation, then how to solve it. So this is L is with u, L of u is equal to some function. So this is a system, because equation were linear. I have taken all the example of linear. You will say, sir, you are taking all the example linear. What is in that? We can solve it very well. But today I'm going to explain the idea that how we can solve the linear first. Then we'll come later on the linear coupled equation. Then I will come on the non-linear equations, how we can solve it. So this is the gradual process of learning these methods. That's why in the beginning we should always talk about the toy problems. So if you can play with some small problems, so definitely you will think about the solution of very complicated problem by using this technique. So this means that you have a L is left hand side and right hand side is F, and the solution you know very well that L is a linear matrix and this is known to you, F is known to you. So your U is nothing L/F. This is simple command of solving. Ax equal to B, A/B is a solution. Now, what is that solution? So I'm going to write the surf command here. Surf F means the surface. What will be the surface of here? So I'm going to run this code. This is your, see the picture. This is the solution of this Poisson equation. Okay. This is your solution of this Poisson equation. Okay. You can rotate and you can see anywhere else. This is your solution. But you are not getting its basically the contour plot. Contour plot means it's basic contours we are going to talk about. So what to do? For this, we are just writing a simple command here. Instead of surf, you are writing surf C. Just see, I'm just changing simple thing here. I'm changing here simple thing. Instead of surf here, I'm taking surf C. Surf C means surface along with the contour. C stand for the contour. So definitely the surface will be the remain same, but the contour will be in your plane. I'm going to show you the graph here. And is it visible? Is this graph is visible?
Yes, sir. Yes. Yes, sir.
So here it shows that this is the contour plots. Okay, this contour says that, okay, this is the basic contour, but this is the surface plot because it's three-dimensional. So this is the surface, that is a solution of this surface represent the solution of the Poisson equation, while at these are the level curve. Contours is nothing but we know when we are going to study some three-dimensional geometry, that level curve. Okay. So these are the level curve means contour C. So this is the process that we can solve any partial differential equation by using the spectral coefficient technique. Okay, so I think the time is okay for 41, 42. So I'm just giving 5 to 10 minutes for the discussion. If you have any problem, then ask to me.
Okay, no problem, sir. Okay.
And definitely I will share all my slides and everything in the group so that you can enjoy and you can learn so many things, because being a teacher, it's my sole responsibility that okay, we should impart the knowledge in front of the audience so that they can enjoy and they can make it useful for their research, for their teaching. So I welcome anyone who may ask any problem related to my basic lecture.
Sir,
Dr. Vinod, yeah,
how
ma'am.
to solve the coupled problem by
Yeah,
using
I'm having one code. I was just asking the same question. That's why I already prepared the code. Okay, so I am a smart teacher because as you have asked this question, okay, I know this solution. I'm going to tell you. Huh? Just wait. Okay, yeah. Let us come in this picture here. So come. The coupled is something written in the coupled. Yeah, this is the coupled equation. This one is coupled. What I did here, I did very simple problem that, okay, I'm going to first explain what is that problem so that it will be very easy. I have taken this one. This is this screen is visible, all of you, to all of you.
Yes,
What
sir,
I have
yes, sir.
considered here, I have taken one research problem. This is a very simple problem in the fluid mechanics. What I'm going to do, we have assumed a steady unidirectional laminar flow in a vertical channel. And that is study laminar, fully developed. So all these mathematical implementation we did, and the whole set of momentum equation and energy equation will come to the two ordinary coupled differential equation. This first is coming from the momentum equation, because the flow is always in the z direction or in the basically y direction, and this is del u by del y square plus Ra is a Rayleigh number, T is a temperature, R is a Reynolds number, P is a pressure. So this is dp by dx is a pressure gradient. And the second equation, energy equation, which is depend upon T d2T by dy square minus u equal to 0. And I'm taking, this is the channel, for example, at this wall of the channel here, the temperature is and velocity is going to be 0, because it's okay, solid, so velocity is always going to be 0. But I'm also assuming that temperature is also 0. And the same thing at the right wall. So it means we have two coupled differential equation. So we need, what are the boundary condition? At plus minus 1, I'm going to 0, u is 0, t is 0. Why I'm taking plus minus 1? Again, because I have to explain
Simplicity.
in the code. Okay? Is the problem is clear to all of you?
Yes.
This is the coupled differential equation. But here is also, when we are going to analytically solve it, here Re into dp by dx is a constant. Ra and Re are input variable, but dp by dx is constant here because we have taken a unidirectional flow, which is fully developed. So it means this is a constant. So when you are going to solve it, that constant will come in your picture, isn't it? But that constant can also be obtained by using the conservation of mass, because mass is cannot be created and not destroyed, as you know very well. So that's why by that we can find out dp by dx. So this is our analytical solution I have written here.
Yeah.
In this slide, this is our analytical solution. We can solve that differential equation, and that this is your analytical solution. We have already implemented in the code. So let us come directly to the code. Here, what are the input variable? Reynolds number, Rayleigh number is there.
Yeah.
K, I have taken for the analytical solution, not to be worried about it. F, you know very well. And now from N we start. N is our order of approximation. Yes. D is our Chebyshev differentiation matrix. D2 we need because everywhere is a two-order derivative. Identity matrix there. Then you just see the equation. I'm directly writing. Means in the first equation is d2u by here. I've written d2u by dy square. It means here it will be double derivative. D2u plus Ra times identity matrix of T. Isn't it?
Yeah.
So can you tell me how many, if we are taking n number of grid points, so n plus 1 point will become from the double derivative with respect to u. You say from u we are getting n plus 1 point, and from t is also getting n plus 1 point because t is also approximated the same grid point.
Yeah.
Okay, so total point will be 2n plus 1. And similarly from the second equation, double derivative
Yeah.
with respect
D2U,
to
yeah, minus u.
yeah. So there will be n plus 1 and n plus 1 from u from t. So this is also 2n plus 1. And the grid point is also varying n 1 to n plus 1 for twice because for u and v. So our whole matrix will be 2n plus 1 cross 2n plus 1. Isn't it? It's clear to all of you?
Yeah.
So there is a two process of solving this one. One is either you are interested to put u first and t second. Or it is my choice. I like T. I don't like U. So I will first T at the first, U at the last. So this is the process. Here, I don't know what I'm taking because it's a simple problem. So let me explain here. What to do is at the first entry, n plus 1 entry, we are going to take from U. And the last n plus 1 entry, we are going to take from T. So that should be think, and it should be keep in mind that at the first positions we are taking U in the matrix, at the second position we are going to taking T. The simple I'm writing A1 is equal to D2, A2 is equal to identity. Why am identity? Just see here.
Minus.
Just see here. This is double derivative. Is there any problem?
Yeah.
No. Okay. This we have taken. First matrix T2 T by dy square means d square, and then with respect to, because we have to take two coefficient. One is a stand for some one variable, b stand for some another variable. Just see.
Yeah.
Okay, so here is we are taking a1 a2, and in the first equation, what is the coefficient of a1? What is the coefficient of a2? In the second equation, we are stand for b. b1 is the coefficient of u, b2 is the coefficient of v. Just see in the first equation, a1 is the coefficient of u. What is the coefficient of u? Double derivative.
Double derivative. Yeah.
So double derivative you are taking here. Is
Yeah.
there any problem? No.
Oh,
What is the basically coefficient of the second one?
minus, that is
Minus
minus
one.
t.
Yeah. So this is minus I. So
Hmm.
b1 is the first equation. So
Hmm.
what is the coefficient of u is there? Ra star I.
And
Okay.
B2 is
Then
B2.
what
Yes.
is b2 is b2.
Yeah.
Now your f1 is
Forced.
force function. We are taking 0 0 because
Yeah.
the right hand side there is one constant. It doesn't matter, but I'm taking that constant is equal to something.
Oh, yeah.
So here we need to find out we need to replace the row corresponding to the boundary condition. What are the boundary condition? At n equal to 1, we will go at the last grid point, but two equation. U at plus 1 equal to 0 and t at plus 1 equal to 0. So two equation will be there.
Yeah. Yeah.
And similarly, two equation for n plus 1.
Hmm.
So here just see, in
A1.
A1 we are going to replace, okay, and B2 we are going to replace because the first one is U and the second one is T. Clear?
Yes.
So now your forcing function, what is that in the right hand side both? 0 I'm taking here, for
Yeah.
example. So I'm going to make a matrix. A is nothing but
Yes.
A1, B1, the coefficient of U.
Yeah.
Second matrix is A2 and B2. And
And
up here F is F1, F2. Just solve it. And you have your solution. Analytical solution I've written here, whatever I'm obtained here. That solution is also obtained by using the symbolic programming. I'm not doing by hand. I'm not doing anything. Everything is MATLAB doing. I'm just using that one. Just I'm going to run it. And I'm going to show you the result. Okay, it's coming. Yeah. Is it clear?
Yes.
Just see here.
Yeah.
Your dotted point will give me the solution at the grid point, while the solid line are giving me the exact solution.
That's all.
Clear?
Thank you, sir.
This is first one is the velocity and second one is the temperature.
Thank you, sir.
Okay. So any other? I'm seeking someone else. Okay. Any problem? Any problem from the any query from the participants? I welcome.
Hello, sir.
Yeah, Mr. Raj, yeah.
Can we solve differential equation by using wavelet transform methods?
Yeah, you can solve. You can solve. Why not? You can solve. You can solve it because if you are using the wavelet transform method, that is also a basically analytical approach. Symbolically, we can use it. Even wavelet can also be used as a basis function. Wavelet function, simply supported function. If you are going to take in the approximation, so simple because in the wavelet function means that there is also a basis function. So if you are taking the simply supported function in the approximation, that definitely your approximation will be by using the wavelet theory, na?
Yes.
Either okay. So we can because people are doing the wavelet finite element method, wavelet spectral method. Several things is coming to the picture, na?
Okay.
Any other, please? Yeah, Dr. Vinod Kumar. Hello. Hello, sir. Hello.
Yes, sir. I'm there, sir. I'm there, sir.
Okay, you are there.
Yeah.
Okay, so
Yeah, we are very much thankful for you, sir, because any information session has given to for our participants, sir.
oh, okay, I have tried my best, yeah.
You are not
Because,
best, more than best, sir. More than best.
if I will be physically there na, and all the participants in
Yeah,
front of me, then
surely. In future,
definitely,
it will possible,
I
sir. More
will
time
explain
is
each and everything. Huh?
Hello,
yeah,
sir.
sir. In future.
Yeah, hello.
Hello, sir. How to
Yeah.
plot vector field in 3D phase portrait?
Can you pardon, please?
How to plot vector field in 3D face portrait?
Yeah, yes, you can plot. You can plot here, na?
Sir, how
How you
can I
can plot, na?
how we
Yeah,
can?
actually, you just go there in the view and or just go to the home. This is a help command here. I'm writing 3D plot here because I have not gone through any book of the MATLAB. Really, I have not gone through properly any training of the MATLAB. Whatever I have learned from MATLAB itself because everything is written in the help. This is the wonderful thing in the MATLAB. This is the, you can say that this is the advantage of this language because this platform will tell me everything in the help. You write just 3D plot and enter them. And it doesn't matter what type of plot you want.
Command window is not visible.
Yeah, that's not visible. Okay, not visible. Now it is visible.
Yeah, now
Yes.
it is visible, sir.
Yes.
Just come to the help command, write 3D plot. 3D plots. There are several things. 2D plot, 3D plot, everything with example will be there. Creating 2D graph. This one is 2D graph. Okay. There are everything in example and the command is also there. No need to go anywhere else and everything will be there. You need 3D. I will just going to explain 3D. 3D plots. Okay, just go back.
Sir, not visible.
Not visible. Okay. Help command is not visible. Yeah, this is visible. It's visible.
Yes.
Is this
Yes,
visible?
sir. Yes.
Just come to the plotting basic pie chart. Everything is there. Contour, 2D and 3D. This is the contour function. This is the way that I'm going to explain here. Just simply expand all. This is the way that you are getting contour, whatever you want. Everything is given in the example. Okay. In 3D also. That's our plot contour 3D, contour 3D. Just come here, expand all. Several examples they have given. Yeah, this is the way. Clear? You can understand from here, just taking mass grade z is equal to some function, exponential e to power minus x square minus y square. This is x is input, y is input, your z is in 3D output. So this is x into exponential this one. I'm just going to copy it. I'm going to copy this one. Control C and directly coming to the command window. Here, suppose I'm taking new file. Control V is there. Control S. I'm just going to save it. Suppose some 1.m. Okay, not 1.m. So cancel. So Control S is suppose a.m. am.m is exist. Okay, no. So I'm writing something a.m. Yeah. If you are just plotting that, it's running this from the editor, run it. So your output is there. Yeah. This is your whatever this output.
Sir, here I want to plot vector field also. Is it possible, sir?
Yeah, everything is possible because
How to add in
also
the same plot?
let me think because I have taken some example through which we can find out the velocity vector field. Okay, that is vorticity vector field. Vorticity is also a vector. So
In a differential equation, 3D differential equation, system of differential equation, we want to plot a phase portrait like a stable system. Then how should I plot this vector field also?
Directly we can just draw here. Similarly, we can draw here vector fields. You can draw the same way in this, but it will depend upon the problem. What type of the functions you are making there, na? Definitely, this will be the 3D. That will be the 3D, na? The two
Yes,
will
sir.
be
Yes, sir. 2D is done, but 3D can't do.
Okay, 3D just similarly you can do. You have to define your vector field, na? Vector field is a function. If writing this is Z is equal to something, this is a vector field, X is a vector, Y is a vector. So this is a vector field. This is defining Z is a vector field here in this plot. Just see here this plot. What is that? If your X and Y is a basically vectors, and this I'm taking Z is equal to in the three-dimensional vector field. Vector field means it's a X is a vector, Y is also a vector, and some function X, f of X, Y. So this is also three-dimensional. In the same way, you can plot it. And if you would like to calculate, that calculation is different, plotting is a different.
No, sir. We want to plot vector field, and is quiver 3 is applicable there?
Already applicable there. Already applicable there, because in the fluid mechanics, what I'm doing, I'm doing the 3D plot where we are also drawing the same thing. That whatever you are saying, the vector field, we are doing the same thing, but we are writing everything in the form of a matrix in our code. And if you send me your problem, definitely I will solve.
Okay, sir.
You just send
And
me your
one
problem.
question. Sir, what is the difference between contour and surface plot?
Surface plot will give me the whole picture of the three-dimensional picture of the plot. Na?
Okay,
As
sir.
usual, suppose I'm taking x square plus y square equal to k square. It's okay?
Yes,
Or
sir.
z is equal to x square plus y square. What is that? That's in 3D. Just see picture here. I'm going to write so you can understand it. Okay, this is nothing but I'm writing here x square plus y square. What is this picture? I will just explain. I'm going to explain here. Okay, just writing CLC because there is some error. Okay, CLC, clear all. Now I will plot it. File line, this is unexpected parenthesis. Okay, this is unexpected. I remove it and I plot it. Yeah, correct. So it's coming. Okay, let me see where is that. First, I'm going to remove it. Unbalanced unexpected parenthesis or bracket. Something is going wrong here. So this is plus x plus y. Yeah, this is with me. I'm going to load this one. This is the picture. Okay. This is a contour plot. Now I'm going to explain what is the surface plot. This is the contour. Everything is given. Na? Z is equal to some constant. This will be the radius. When Z is going to be increased, then you are having the circles. Okay. X square plus y square equal to Z. When your Z is fixed, that is you are taking a cross section. That cross section taken, it is a circle. So these are the all circle, and you can plot it. This is the surface plot, but this is not exactly surface plot. This is a contour which is showing. Na? I am going to change this one. Instead of contour theory, I'm writing mesh. I'm writing surf. Just see in the surf what we are going to do here.
Will be on the surface.
It's not coming. Surface is not coming. Just see here. I think something is in where. This is wrong error updating the surface. Okay, not surface, so surf C. XYZ, not XYZ 30. Not 30. Getting data something. Just a minute. I'm just going to talk about the surface plot Poisson. This is a surface plot of X, Y, Y. Mesh grid is there. So where is our code? This is AMM mesh grid of X. Okay, X versus X is this X square plus Y square, Z is equal to this. This would be there. Yeah, it's coming. It's coming now. I'm going to show you. Yeah, this is this. This is the surface plot. Is it visible?
Yes, sir. Yes, sir.
This is the surface plot, and in the below that you are having the all the contours as you have seen previously. This is the way that here is both thing. One is a surface as well as contour. Just actually it's taking some time. Just I'm going to rotate it. Yeah. This just see there. This is your surface, and you also have the level curve. Level curve is a contour. All are the circles. Clear?
Yes, sir. Okay. Thank you, sir.
Any problem?
And sir, how plot mesh grid in 3D?
Mesh grid.
How to calculate X, Y, and Z axis?
X, Y, and
Z axis in 3D.
yeah, definitely calculate what you want to calculate, or you want to plot it.
Now I want only calculate how to calculate in MATLAB X, Y, and Z axis.
How can we evaluate X, Y, and Z axis? From where we would like to find out X, Y, Z?
In x-axis row wise and in 2D we plot mesh grid. First
Okay. Okay. You want to do numerically how to do it. Just see here.
numerical I want answer.
Yeah, it's okay. Okay. I understand your question. If I understand, then just I'm going to explain one thing here. Just come to the code. This x is equal to -2 to 2. Is there?
Yes, sir. Yes.
-2 to 2. I'm taking the basically the size is 0.25. Difference is 0.25. This is x array.
Straight line.
This is x axis. I'm taking x axis also same y axis. Just see here, mesh grid x is nothing but x comma y, means this same x axis is taking in at y axis. If you want different, then you will have a different. I'm writing y here. Y equal to suppose -3 to same thing 0.25 okay to 3, isn't it? If you are writing y here, then this is a mesh grid of x comma y, nothing else. And just run this code. I'm going to show you the picture. This is your picture here, isn't it? Your space is going to be changed, or your x-axis already calculated, y-axis already calculated, and then z is equal to, we have defined x square plus y square. So that's why this function is coming to here. It's clear?
Sir, numerical value, please.
Okay, numerical value. Yeah, just see x here.
Only, sir, mesh grid.
Mesh grid.
Yes, sir. Yes.
You just write here capital X. You will have x. Already calculated here. If you don't want to calculate, there is a workspace. Just see in the left hand side. I'm going to share this one. There is a workspace here. Where is my cursor is moving? Have you seen this?
Yeah.
This cursor?
Yeah.
This is X is already here. Y is already here. Everything is here. Small x is also here. Just see in the row. And Z is also here. It's okay at every point. So everything already generated here. You can use also calculate as a numerical values. Isn't it?
Yes, sir.
Okay, I don't know how much you are getting from my lecture, but I've tried my best or through online because it's a very big difference between the physically if I will teach you and through
Yes,
online
yes,
we
sir. No
also have
problem,
so
sir.
many problems.
Till now we are happy, sir, because of you.
Yeah,
Till now only we are so much happy, sir. In future I will plan, sir. Offline, not offline.
I don't know. Okay, I'm not seeing the chat box now.
Yeah. Anyway,
Okay,
thank you
okay.
very much, sir, for your
Okay,
valuable
so
time.
so thank you very much for inviting me for just interacting with the new
Yeah. In
and
future we'll
young
organize one
researcher.
more program with you, sir.
Definitely. I'm always free. Okay.
Yes, sir.
So
Okay, sir.
I'm also thankful to all the audience who are
Thank
listening
you so much,
me
sir.
very peacefully, and I'm also very happy that I'm getting so many response from the audience. That is also good for me because this is the platform that we are learning together. Okay,
Yes,
we
sir.
are not
Thank
showing
you.
that we are so much intelligent. We are just here, just learn to each other. We are learning from each other. Okay.
Okay, sir. Thank you.
And anytime you may contact to me if you have any problem related to your research
Sure,
and
sir. Sure, sir.
you are solving some problems. Okay. So
Okay.
can I move? Can I leave from this?
Yes, sir.
Okay?
Yes, sir. You can, sir. Okay. Yeah, participants, don't worry. In within 10 minutes, I will send the certificates to Drive. So you can check your certificates through the list which I have given earlier yesterday. So that any changes regarding certification, name, affiliation, or anything, you can post me separate to WhatsApp. The reference of your ID, your name and designation is your CSSR ID, which is provided right side. Okay.
Sir, actually,
And-
my name is not there. My name is Mridula Kanoria.
Yeah, I know, madam. I know, madam. Don't worry. If those names who don't have in list, I have separated and I will send the certificate to personally. Don't problem. I will send to everyone, but certificate is guarantee.
Okay. Yes, sir.
Okay.
Thank you.
Thank you, madam. Thank you for all your cooperation, madam. I think everyone is satisfied with the programs, madam.
Yeah, it is really very
Yeah.
encouraging. Actually, we are not doing in the MATLAB. We are doing in something in the mathematical.
Madam, one more thing I want to tell to all the participants who have at least 40 members. Next time I am going to conduct a Scilab.
Acha.
This is also similar to MATLAB. This is useful for drawing graphical methods like that. I will announce